Hello, everyone, and welcome back to the FUNWAVE application on the ETA DEP HPC portal. In this video, we're still working through the third tab of our simulation workflow, that input-output tab, this time focusing on the physics and numerics fields of our simulation. Here, we will briefly discuss the concepts of the physics and numerics parameters. Now, this is the 6th video in our FUNWAVE application video tutorial series. If you haven't already, please check out the introductory videos covering previous sections of this simulation workflow, as well as a general overview of this application as a whole. As always, tune into the FUNWAVE Comprehensive Wiki to learn more about the model and its input parameters. And just as a quick reminder that the example we've been working through is a two-dimensional simulation using solely the central module. Keep in mind that any other simulation or any other module you would use for a different simulation, for example, like ship wakes, you would also have some additional capabilities and features in the inputs tab that are module specific versus just those that are seen in this central module here. So with that, let's chat physics and numerics. Now, for a regular user, when you enter this section, you only see a specific number of options. And these are the fundamental variables you'll need to consider, and that which we'll be covering in this video. So starting with the physics section, the first variable is dispersion, which is part of your numerical code. So generally, dispersion should be turned on, and you do so by checking this box. Once it's turned on, these default values appear for the 3 dispersion parameters, each of which are set to 1 by default. These are gamma 1, gamma 2, and gamma 3. If you are unfamiliar with these dispersive terms, you can hover over the info icon for more information, click on it, and be redirected to the wiki for details. So if we do go to the wiki, there's detailed information of what these variables mean and what happens in the physics if you change them. For example, in your simulation, you might be using the fully nonlinear equations and everything is set to 1. Or if you are familiar with the weakly nonlinear formulation, you can run those equations that are the same sets of equations contained in Boost 2D by setting gamma 1 to 1 and gamma 2 to 0. Now, I'll leave that there, but you can continue reading through the specifics if you are interested. There are other parameters listed in here that are related to reference variables, which may get a little in the weeds and quite technical. So if you do have questions, you can always contact us via email. And do remember, back in the portal page, we do have access to this expert help and bug reporting button, so you can submit your questions to us via email. So back in the portal, moving on to the next variable in the physics field, we have viscosity breaking. If this variable is not checked, the model will use one of its standard shock capturing type breakwaters. And there are pros and cons of using one versus the other. Viscosity breaking is a little more involved and technical, so we generally recommend to set viscosity breaking to true and to stay with those default parameters that come up. So if we check this, we have 2 parameters, cbreak1 and cbreak2, that have default values. Now, if you do want more information, again, hover over that info icon to go directly to the wiki, which will also point you to some other publications going back to Kennedy and others from 2007 and similar that explain the reasons behind these default parameters, default values. Next, we have this SWE ETA DEP variable, and this is set to a default of 0.8. You can change that, but essentially this variable is the ratio of wave height to water depth for which, from switching Boussinesq type equations to the nonlinear shallow water equations. So once that ratio gets to a certain point. Now this variable is specific to the shock capturing scheme. However, if it's not going to be applicable when you choose the viscosity braking, then you won't have to worry about that since we do have viscosity braking on. Next is this frictional matrix field. Here you can give your bathymetry some friction parameters, and this is typically the quadratic friction. So currently when this is not selected, for example, you still have the option to set a fixed friction parameter applied to the entire domain if it's a non-zero value. So for example, if we change the CD fixed value from 0 to 0.002, for example, this would be the value of our frictional dissipation parameter across the entire domain. Instead, if you do use the friction matrix and you set this to true, you will be prompted to upload a friction file. And similar to your variable bathymetry file, this will have the same size as your grid, the same size as mglobe and nglobe. And each value in this matrix, which is in an ASCII file format, is the value of the frictional parameter, so that CD fixed parameter, in that area or subregion. So essentially, this gives you a non-homogeneous, spatially variable frictional parameter over your domain that you can include. So we'll just uncheck that for now. And lastly, in this physics section, we have the periodic boundary condition. Now, this is only available for a two-dimensional simulation. This is only a two-dimensional feature, so it would not be available in your one-dimensional simulation. If you do select this feature, the north and south boundary of your grid or of your simulation would be periodic. So essentially, any waves that exit the north boundary would continue to propagate up through the south boundary and vice versa. And here, the north and south directions are relative to your grid, not geographically oriented or referenced at all. And you can find more info on this, again, by hovering over that info icon and reviewing some more details on the wiki. Finally, let's briefly go over the numerics section. So currently, there are 3 variables listed in this section here. However, we would like to note that if you are a more advanced user and you've registered with us as an advanced user, you're familiar with the physics and numerics of this model or other numerical models, you may have the option to access more variables in this section at your own risk. For example, in the numerics field, while there are only 3 variables listed here, there are other variables that are a little more specific. And if you know what you're doing at your own risk, say you want to choose a different numerical method or time step integration, you can manipulate those variables as well. Some of those options would be available to you here if you're registered with us. Please send us an email if you are interested in that option. Otherwise, there would be an option for more advanced users to directly edit the input file in the Run tab, in the 4th tab of our simulation workflow. And we'll discuss that in more detail in a subsequent video tutorial as well. So back to the 3 variables in the numerics. The first is the CFL variable, or the Courant-Friedrichs-Lewis condition. It is a numerical stability condition that must always be less than 1 for you to have stability. One thing to mention about this variable is if your simulation does happen to be unstable, maybe some short waves are being excited and so forth, the first thing to do to try to stabilize the simulation is to lower the CFL condition. For example, you might want to change this from 0.5 to 0.25 if you're experiencing instability, and see how that goes. Next is this Froude cap variable, and this is a limit for the Froude number, where the Froude number is the ratio of water velocity to the shallow water wave speed GH, gravity times water depth. Now, lowering this number may come in handy, for example, if your simulation involves run-up and overtopping studies, which requires wetting and drying of topography and things of that nature. So if you do have shooting jets down on the other side of a levee that's flooded or overtopping occurred, there may be high velocities, and this parameter may need to be lowered to handle those velocities and to increase stability in your simulation. Lastly, this minimum depth variable, this is minimum depth in meters, means that any submerged point that is less than this variable, less than this value of water in the vertical extent, will be considered a dry spot. So this is currently set to 1 centimeter. So that means that any layer of water in your domain that is less than 1 centimeter in depth vertically, or whichever non-zero value you have here, is immediately made dry. It's kind of a default drying condition almost. So with that, we did have a brief overview of the physics and numerics fields of the input and output tab of our simulation workflow. This concludes our tutorial on this field, and we do hope that this was helpful. Please always remember to save your changes with this red save button in the bottom right corner of your screen. And if you do have any questions, feel free to check out that wiki or contact us via email. Happy modeling!